Okay, my name's Dave Lester. This is the first of the lectures I'll be giving as part of the ICT course for the Human Brain Project, and it's what I regard as the core of practical computer science. So this is not programming, this is how we analyse programs, and it's called asymptotic analysis. And I'll explain why it's useful and in limited cases how we go about doing it. So the learning outcomes we want to get from this will be described. I'm going to talk about average case and worst case analysis of a program's runtime. I'm going to talk about the order of growth of that runtime. I'm going to talk about the properties of big O, which is a notation we use. And finally, I'm going to talk a little bit about the lower bounds on problems. So at the end of the material, you'll be familiar with a very simple programming language. It's like a cut-down version of Python, and so it's a little bit different, especially with the syntax, but try not to worry about that too much. We're going to become familiar with methods to analyze the efficiency of algorithms written in an imperative programming language. Bear in mind that Python can certainly be used as an imperative programming language, although it does have other features. So if you're going to use these other features, you need to, and you want to do analysis, you're going to need to think a bit harder about things. We're going to use the big O notation and its relatives, big omega and big theta, and we're going to understand the relationship between these ideas. So let's get going. Here's the very simple programming language that we have. I'd like you to look at the first line of this grammar because it's really telling you the facilities that are available within the programming language. What we have are assignment, that's the first one, and I'm using the old-fashioned Pascal notation of colon equals to form an assignment. Skip, which is the statement which does absolutely nothing, turns out to be a useful program. Sticking two statements together with a semicolon between them, unlike Python and C, the semicolon is not a terminator, it doesn't occur at the end of every statement, it merely joins together, splices together two statements. Then we have a conditional statement which tests a Boolean condition, little b. If the condition is true, then we execute statement S1, otherwise we execute statement S2. And finally we've got a looping construct which loops round while the condition holds true. If the condition is true, we keep looping and we execute the loop body S. When the condition becomes false, we drop out of the loop. I'm not going to say very much more about the Booleans and the arithmetic expressions because I'll feel free to extend them a little bit to make the programs that I write a little bit easier. So the non-terminals here, if you want a little analysis of grammar, the non-terminals are the things that can expand up into other things. They're capital S, little b, little a, and they represent statements, Boolean expressions, and arithmetic expressions, respectively. There are certain terminals, that's fixed things, which are the keywords and symbols such as plus, and the variables and the numerals. And we can use dashing or subscripting to represent different ones. We'll feel free to extend this very simple language with extensions such as array, expressions, and assignments, and we'll see that shortly. And we're also going to use a for next construct to represent some of the while loops. So let's have a look at a first program here. We're going to add two matrices together. Matrix A plus matrix B is added together and the result is placed in matrix C. And the structure for doing this is to iterate over first I and then J, do the addition, which is the third line there, and place the result back in C. And the reason for talking about this now is we're going to analyze this and see how long it takes. So we're going to count the number of additions for the input matrices of size n by n. And the way you always do this is to start with the inner loop and work outwards. So looking at the inner loop here, it's going to manipulate variable j, and it's going to execute n times. It starts with j set to value 1, and ends when j is value n, so it's gone round n times, and each time it goes around the loop it does one addition. So we've performed n additions in total. Next, you observe that the outer loop, which manipulates the variable I, has a somewhat similar feature to it because it too executes precisely n times, and the loop, however, incorporates the one for j, and thus there are n additions in the loop for j, and you're executing that loop n times, so that's n times n, and that's the total. So in order to add two matrices of size n times n together, we need n times n, or n squared, additions to be performed. Just in case you're thinking there's a pattern here and that the number of operations performed is dependent on the size of the matrix, well, it is, but if we were to do the same thing for multiply using the simple multiplication algorithm for matrices, it would turn out to be n cubed. So you need to be a little careful here. Not everything is n squared. Now I want to say a little bit about average case and worst case analysis. Suppose that in this case we want to find the index of the first element in a one-dimensional array. So by that we mean a list. First element that's bigger than a particular value m. So we can use the following program to perform this task. You set the index 0 to be 0. You set I to be 1, and while I is less than or equal n, and the array value is less than or equal m, you just increment the counter I, and when you get to the end, you set the index to be I. And that's how you can calculate the value of the index of the first value that's bigger than m. Now, if you're really unlucky, all of the elements in the loop are less than or equal to m, and you won't be able to tell that until you've inspected each and every one of them. So you'll in fact be, in the worst case, looking through the entirety of the array without finding the value you're looking for. Another alternative is that it's actually the first element that turns out to be the one you're looking for. And then, of course, you're only executing the loop once. So that's the best case. So we've had a look at the worst case and the best case. Depending on the precise distribution of the elements of the matrix A, you may be able to give an average case. Now, I want to caution you here to be very, very careful. We need to define what the random distribution of the elements in the matrix is precisely before we're actually able to say anything about what the average case is. The reason for me emphasizing this is that quite often people will say, the distribution of the elements is completely random, and then make an analysis based on this. And it turns out that, in fact, they're using the matrix or algorithm that they have at hand in ways which are in violation with the random distribution that they've assumed. So it's often possible that you want to sort a list, and you assume that the list is completely disordered, randomly ordered, and in fact it is completely ordered, and if the sorting algorithm takes a longer time, like quicksort does on a sorted list than it does on a randomly sorted list, and your assumption is violated, then it'll take n squared instead of n log n. So, in our case, if the elements of our matrix are independently normally distributed with mean m and a non-zero variance, so about half of them will be less than m and half of them will be greater than m, and they're sorted into ascending order, then you'll expect to search just half the list. Be very careful about assuming lists are random. This is just a repeat of what I just said, because if they are ordered, this can have a bad effect on the performance. And really, really important here, be very careful about assuming your data is actually random. It's very easy to repeatedly sort lists which are already partly or fully ordered, and when that happens, the properties that you're expecting no longer hold, and the algorithm behaves rather worse than you were expecting. Okay, so that's how to analyze an individual program and count individual operations, and how we can talk about the average time and the best case time and the worst case time. Now I want to talk about orders of growth. And here, what we have in mind is we're going to use a notation which abstracts away from the precise count and just counts the significant parts that we're interested in. So unless we've got a particularly strange instruction set, say a one-cycle quicksort instruction, there's usually a relationship between the size of the input and the amount of time it takes to run the algorithm. In other words, the bigger the input, the longer it takes to run. So what that means is we're going to ignore constant scaling factors for the time taken. In other words, if the algorithm doesn't run quickly enough, buy a new machine, buy a bigger machine, buy a better machine, and you should be able to get the required performance by buying a slightly better machine. So let's consider two functions now, which are both taking natural numbers to natural numbers. The first, f of n, is the identity function. It takes a natural number, and that's the answer you get. And the second function is g, which is the quadratic function, which is taking a value n and squaring it. You get n squared. So it doesn't matter in this case which value of n we select. It'll always be the case that g is bigger than f. And the reason is that n is always less than or equal to n squared. So in this case, we can say that n squared dominates n. It's bigger than it. Now let's have a look at another pair of functions. This time we've got 100n, and g is exactly n squared as it was before. Now we get a slightly different pattern of behavior. If n is less than 100, then this time the function f is actually the bigger of the two in that range. For example, at n equals 10, you'll get 1,000 for the answer for f, and only 100 for the answer for g. But eventually, g becomes bigger than f. And in this case, eventually means for any value bigger than 100. And of course, other functions, you can get a similar pattern of behavior occurring. Eventually, one part of the equation will dominate everything else. So here's the thing put down in a formal logic form. There's no actual reason why you need to know this particular part, but if you want some practice at logic, it's here. So what we're saying here, if you read the logic line, it says, for every n, this is the definition of eventually dominates, provided n is bigger than some k, then g of n is bigger than f of n. In other words, g of n dominates f of n. This observation is the thing that allows you to ignore functions that are eventually dominated by other functions. So putting these two observations together, we arrive at the following very useful conclusion for polynomial complexities. That is, if you have a time complexity that is a polynomial of order k, then you can ignore all the terms k minus 1 down to 0 and delete the leading coefficient. So all you get left with is n to the k, the biggest power in the polynomial. And that makes for a very useful way of simplifying the terms for a time complexity. It both makes it easier to do the analysis and easier to do the to present the results at the end. So, having discussed the big O notation and why it's significant and important for us, in this section I'm going to demonstrate some of the properties of this notation. You should be aware, by the way, that some people are quite informal and sloppy about the way they use this, so you just have to be prepared for that. In particular, instead of writing the function properly, you can often see things like O1 and On, and these are actually shorthand for the polynomial functions f of n equals 1 and f of n equals n. So that's the constant function 1 and the identity function. So the first of these properties is that the function is a member of the class of functions which are related to f. So that's what the big O notation is doing here. It's expanding f itself into a set of functions to which it's related. And the proof here, given the definition we had earlier, is to pick k equals 0, which means we don't have an e eventually, and c equals 1. And then we discover that for all n, f of n is equal to cf of n, which is less than cf of n. So that gives us the result we're looking for. The next thing we can do is show that there's a strict set of hierarchy being induced on these sets. So the set of constant functions are a strict subset of the linear functions. And here, again, if we expand out the definition of the big O notation and fill in the correct values here, everything works correctly. And the proof is in the notes. This is the one that is particularly important. If you have a polynomial and you want to take the big O of the polynomial, the simple thing to do is to cross out all of the smaller terms and delete the leading coefficient ak. So, we would normally simplify the set big O of g as big O of n to the k. And finally, in computer science, we quite often have logarithms appearing, and that sits nicely between the constant functions and the linear functions. I should note, by the way, that logarithm is usually taken to mean logarithm base 2. It's normally because we're just splitting things in half. Okay, that covers the big O notation. Well, no, it doesn't. There's lots and lots more about big O notation. But it's the way that computer scientists think. That's why I said this was perhaps the most significant and important of the lectures I'm giving, is that it actually gives you an insight into the way a computer scientist thinks about problems. They're really trying to analyze problems and decide how cost-effective the solutions they come up are going to be using a big O notation. So you'll hear them talk about linear or quadratic algorithms, or quasi-linear, that means n log n. And what they're really saying is the problem scales according to the size of the input data. So if the problem scales according to a constant function, that means no matter what size of data input you have, it's always going to take the same time to calculate the answer. That's a nice problem to have. The next one is linear. And that means that every time you double the data set size, the computer is going to take twice as long to run. That's probably okay. The next one is n squared. Let's go up in polynomial form here. And there you've got a problem in that if the data set doubles in size, the computer program is now going to take 4 times as long to run. And this is beginning to get problematic. If you can imagine that you have a problem which works for a petabyte, and now you want to work for an exabyte, and it's an n-squared algorithm, that's going to take 1,000,000 times as long to run. This is very bad news. Now we're going to look at lower bounds. They're related to the big O, but the big O notation is describing the complexity of the algorithmic solutions, whereas the lower bounds we're looking at now is describing the fundamental size of the problem. So in this case, we're talking about lower bounds. We want to say that any solution to a particular problem must take at least a certain amount of time or size. So here's the definition of capital omega, and all that's happened here is that we've inverted the order of f and g in the final line of the definition. So we're now talking about something which is less than f of n, less than or equal fn. So here's the important take-home messages. Algorithms have an upper bound on their execution time. So quicksort has an average case order n log n, that's quasi-linear. And problems have a lower bound. Sorting must be capital omega n, since basically you've got to look at each element at least once. You don't know whether you've got the thing in order until at least you've looked at them. The problem here, as you can see, is that there's a difference. So the problem's lower bound is linear, and the best algorithm that we know, quicksort may not be the best algorithm, but the best algorithm has the same complexity here of n log n. And this gives rise to algorithmic gaps. So if the best algorithm for a problem has the same complexity as the problem complexity, then we have, in some senses, a near-ideal program. We've written a near-ideal program. I should caution you that this doesn't happen very often. The vast majority of programs and problems, there is always an algorithmic gap. So that's much more common. It's not a problem. It suggests one of two things. It suggests either there's a better algorithm out there and nobody's discovered it, or alternatively that the proof of the problem's lower bound is incorrect and there's actually a better lower bound out there. My suspicion is that normally it's that. We've probably got pretty good algorithms for a lot of things, not everything, but a lot of things, and it's more likely to be that the problem actually has a slacker lower bound. So let's talk about binary search. This is an example where we know there's no algorithmic gap. To search a telephone directory, we've got to translate my name into an integer. So let's pick an integer here. 1,147,237,989. I don't know why I chose that. And then we use a while to set a variable to be my name, which is this number that we've just invented, and then look up in the telephone directory to try and find the phone number. What's the best we can do here? Well, somewhere there has to be something in the program which is going to make an assignment that the value that we're looking for is 55726. But before we get to this, we've got to select a path through a tree, which in the case of the algorithm that we've been looking at has an if-then-else construct, and so we're splitting. And to minimize the number of comparisons, we need to make the first comparison split the space into two equal parts. And you're going to repeat this procedure, and after 20 comparisons, you can have over 1 million different possible telephone numbers stored. So the number of comparisons is doubling at each point, and when you've got 20 comparisons in there, you have 1,024 squared is actually the number of telephone numbers that could be in that telephone directory. And this corresponds intuitively to if you were looking up somebody's name in a telephone directory, you split the telephone directory in half and probably find my name slightly before the halfway point. But you look on the page halfway through the telephone directory and it says M, a surname beginning with M, and you say, well, I can't be needing to look in the top half, I'll look in the bottom half. And you keep repeating that procedure until you find my name. So searching a telephone directory, the time complexity of the best known algorithm is order log n, and that's the same as the lower bound for the problem, which is omega log n. So we've got no algorithmic gap in this one particular case. I should caution you that this is probably the only algorithm and problem where we know this to be the case, other than something even simpler, and that, for example, for sorting, it's a linear big omega and a quasi-linear best algorithm at the moment. And my suspicion is quasi-linear is actually the lower bound on the problem complexity, but nobody's been able to prove that yet. So, a conclusion. We've introduced a very simple programming language. We've seen how to analyze simple programs with loops and give the complexity. We've discussed algorithmic complexity and why it's useful. And we've introduced the idea of lower bounds for problems and discussed algorithmic gaps.